well, because then I can pause. Okay, so now we are to like day 3 of organic chemistry. So I need to come back where we are. Okay, so then what you just did for me for the quiz was help show me where you're at understanding like how we draw molecules out. And so if we're given a structure, how can we draw them out? What I think probably most of you found was that if I have you do like the literal Lewis drawings with like dots and lines and have to draw out every single hydrogen atom, that gets really, really tedious, right? Really tedious. And that's the whole point of line angle drawings. So the whole point of line angle drawings, let me go ahead and put this in presentation mode, is because then I can go ahead and just like scribble. Oh, technology might be failing us. I may have too many things going on at one time. Oh, it's not giving me. Okay, so I'm going to try a different annotation. There we go. So then I can just come in and go, whoop, and then, you know, I've represented a carbon chain. Or I can go like this. Okay, so I have a carbon chain, and then it's double bonded to an oxygen. Okay, and so then that's the advantage of the line angle drawing. We can make very quick drawings. We don't have to worry about drawing in every C. We don't have to worry about drawing in every H, but they are implied. Let's do just a little bit of work backwards with this problem so I can make sure that everyone kind of understands line angle. So right here at the end of my line, so right here, I have a carbon. So it is implied at the end of the line. How many carbons must, or how many hydrogens must that carbon be bonded to? It must be bonded to 3, absolutely. Because how many bonds does carbon form? It forms 4. So I know there are 3 bonds right there to the carbon. So let's go to like right here in the middle. So right here in the middle, I have that carbon. How many hydrogens is that carbon bonded to? Yeah, 2, exactly, because I can see 2 lines, I can see 2 bonds explicitly drawn. That means there are 2 implied bonds to hydrogen atoms. Okay, so now a trick question. Right here at that angle, I certainly have a carbon. How many hydrogen atoms is that carbon bonded to? And everyone in the room in front of me is shaking their head no. So it's none. Because I can see explicit in the drawing is that there are 4 lines, so 4 bonds. How many bonds does carbon form? 2. And so there are no hydrogen atoms at that position. Okay, great. So we are getting a really good handle on our different kinds of ways to draw and how to read a line angle drawing. Okay, so we're going to go ahead and move forward. So we've done that, and I have here, we need to do more practice in drawing. So the textbook has drawing problems. Canvas has a link to some online practice problems. And then you do have another drawing assignment for this week. So for the next week, so between now and next Wednesday, I have an online worksheet for you to work on. And so then this is called like the functional group and naming worksheet. So on Canvas, you'll see this as a second assignment. So on the Canvas page, you have the class presentations and then the class assignments. And underneath class assignments, you have the syllabus quiz, which is due today or due tonight by midnight. And now you have a new assignment called the functional group and naming worksheet. And so between now and next Wednesday, you will work on this worksheet on your own. I say on your own, but does it have to be literally independent? No, all worksheets are open to working with each other. Okay, and so it's a little different now because you don't necessarily see each other from day to day in the building. So remember that at any time you can create your own Teams meeting between a couple of you. You can create your own Zoom meeting between a couple of you. You can come to my office hours. The Chemistry Coaching Center opens on Sunday. And so then there's lots of different options on how you can meet with people. Okay, and so if you're wanting to put together like your own little study group and not quite sure how to do that in Teams or in Zoom, let me know. Because it's actually very easy to set up your own little study group and then meet together online to study together. Okay, so moving ahead, what I promised on Monday is that now we're going to move into what about molecules, atoms with charge? What do we do about charge? So first, I want to work on how do we know what atom is charged? So what I have here is an example problem, and I'll bring up my annotation again. Okay, right here with this practice problem is I have a molecule drawn, I have brackets around it, I have an electron highlighted. So that means we have done chemistry and an extra electron has been added, but to where? Right, so with this drawing, I'm not telling you where that extra electron exists. So let me tell you how I solve for charge and figure out what atom is holding the charge. Well, I know every hydrogen, oh, I didn't mean to move that. Every hydrogen forms how many bonds? It forms one. And then every carbon forms how many bonds? It forms four. Okay, and now everyone, even at home, out loud, how many bonds does nitrogen form? It forms. And yeah, very good. And then oxygen. Someone online, how many bonds does an oxygen form? Or someone in the classroom yell out, how many bonds does oxygen form? And everyone says 2. Okay, so then I just look for that. So I come over here, okay, this carbon, yep, it's good. So check mark. It has 4 bonds. This carbon, do I see 4 bonds around that carbon? I do. Oxygen, do I see 2 bonds around that oxygen? I do. Okay, oxygen, oh no. What do I only have here? 1 bond. So it does mean that absolutely my oxygen must be the atom with the charge. So that's how I solve. So I just look for patterns. I am all about patterns. And so I recognize that this oxygen is not in its normal pattern, therefore the oxygen is charged and has a negative charge. Okay, so that's my way that I solve. There is a mathematical formula. Let's go ahead and work through the mathematical formula. So I'm going to, I think I can do this, take away all my scribblings so that then I can add more scribblings. Maybe I'll change here to a different color. Let's go blue. Maybe I can go to blue. No, we'll leave it red. Okay, so here's the math. So for the atom, count the valence electrons. Okay, so oxygen, how many valence electrons should it have? Not how many are drawn into this picture, but how many valence electrons does oxygen have? It has, so normally uncharged, it has 4. So oxygen normally has 4 valence electrons. Okay, and so then, now I'm okay, so then we subtract non-bonded electrons. Okay, and so then how many, this is when I should go back in the video, erase, come back, of course. In my mind, I am thinking, let's see, valence, how many valence electrons does, I'm jumping between my atoms in my mind. No, I was right. So how many valence electrons does oxygen have on the periodic table? Absolutely, it has 6, right? I had jumped in my mind to step 2. My brain is going too fast. Okay, 6 valence electrons minus, how many non-bonding electrons does this oxygen have? And so what I can see is I have 3 lone pairs. So how many non-bonded electrons do I have? I have 6. And then I subtract from it half of the bonded electrons. So 1/2 times. And then so I show 1 chemical bond. 1 chemical bond holds how many electrons? 2. So it's 1/2 of 2. And so then that would be 6 minus 1/2 of 2. And so that oxygen has what kind of a charge? It has a -1 charge. Okay, so there is math that we can do to determine a charge, but I personally look for patterns. And so what I know, I can summarize. So like what I know is carbon. If it has 4 bonds, it's neutral. Okay, so if it has 3 bonds, so I'm going to put a B for bond, and it has 1 lone pair. So I see a lone pair, then I know that actually the carbon has a negative charge. Okay, but if the carbon just has 3 bonds and it doesn't have a lone pair, then what would be its charge? If it's not negative, it therefore must be positive. Okay, and so then that is the pattern for carbon that I look for. So I look for 4. And then if it's not 4 bonds, I look for, is it 3 bonds with a lone pair, 3 bonds without a lone pair? And then it's either plus or minus. Okay, so on paper, I can draw a carbon with 2 bonds and 2 lone pairs. Sure, I can do that on paper. And we could figure out the charge. But is that ever regularly observed in an organic compound? And the answer is no, it's not. And so then that's why we're not going to even worry about what if carbon has 2 lone pairs, that's going to be its charge. We're not even going to worry about it because it's not something that we usually see in nature. So of course, all the time, chemists are doing new and funky things with atoms. And so out there in the research world, is there a carbon with a 2 minus charge? Sure, in research. But we're mostly addressing like what are the standard organic compounds that we see from day to day in this class. And so we're not going to get into some of those patterns. Okay. Yeah. But so no, because it would be, yeah, so 6 minus 6 is 0, right? And then if you take 0 and then minus another 1, then that's going to give you a total of -1. I think you're trying to do a double negative in your math. Does that make sense? Right. And so if you did that way, that would be 6 minus, and then it would have been a 6. So then I think that way, yep, it would have been a plus. Yep. Yep. If you're doing it by that method, it would be, because you're doing 6 valence electrons and then minus from what are all of the other electrons. And so then that would have been the math equation that you used before. And this is what, yep, exactly. Yep. And so that's why instead of even worrying about math, because you're right, almost every Gen Chem teacher can teach a little bit different math. I have gone totally to just looking for patterns rather than worrying about the math. And so then let's think through just a little bit about oxygen. Okay, so if I have oxygen, again, we've already established its normal bonding pattern is that it has 2 bonds. And then it would have 2 lone pairs. So it has 2 bonds, and then it has 2 lone pairs. Okay? And so then what if oxygen instead only has 1 bond, and then it has 3 lone pairs? Then what charge is that? What did we just figure out? What is that charge? It has to be it has to be a -1 charge. Okay, and then that's going to be the most common form of oxygen that we will observe. So sure, I could draw out a bonding pattern for what if it were positive, but that is just not going to be an as likely charge state that we're going to observe. Okay, and so then that is kind of like the little bit that I wanted to do with charge. I guess before I totally move on, what I want to go ahead and mention is that a lot of what we begin to do in organic just becomes logic. So is there math involved? There can be, and really fancy ways to solve things. We begin to just think about something logically. So I want you to go ahead and take a look at this other picture that I have. And so then, this one right here. Okay, so we've just established that when an oxygen is 1 bond and 3 lone pairs, it's negatively charged. So that would mean this oxygen is negative, this is negative, this is negative, and this is negative. And so actually that would be a 4-. But here outside the brackets, it shows that it's a 3-. So what else must be going on in this structure logically? What else? Go ahead.
P must be charged positive.
Exactly. The phosphorus must have a positive charge, right? Yep, that's exactly it. Could we use the math and solve for that? We could. But some of this we just do logically. Okay, and so then that's what I want to first introduce about formal charge. So now, but I need to bring things all together. And so then here's another problem that I want us to think about. So what if, I'm going to try going to pencil. Oh, I like that much better. I'm going to go to pencil mode. Okay, so at the top of the page, I now have a line angle drawing. And I'm going to choose like this 3rd carbon here from the end to be positive. Okay, so that carbon has a positive charge. So is that carbon bonded to any hydrogen atoms? So now this is where we have to begin to bring concepts together. So carbon normally forms 4 bonds. And so if I look at all of these other carbons along this line angle, I would know all of these other carbons are like bonded to 2 hydrogens. So then there's another hydrogen here, there's a hydrogen here and hydrogen here. And so what about this carbon? Is it bonded to how many hydrogens since it has a positive charge? Yeah, go ahead. So it is bonded to 1. So, yeah, and so this is again kind of recognizing the patterns using the logic. So a positively charged carbon is 3 bonds, no lone pairs. Since 2 bonds are shown, then that means that carbon absolutely is bonded to only 1 more hydrogen atom. It is not bonded to 4 different things. It does not form 4 bonds. It is bonded to just 1 hydrogen. Okay, and so then let's see if I can figure out all of these annotations. Oh, I did get it to purple this time. Okay, so then what if I do let's see, I'll go here and oxygen negative. Okay, I have a carbon chain, and then bonded outside the chain is an oxygen that is negative. Okay, and so does that oxygen have lone pair electrons around it? And if so, how many? So everyone in the room, for you at home, is shaking their head. Yes, absolutely, oxygen has lone pairs. How many lone pairs does that oxygen have? What is our pattern for an oxygen with a negative charge? And again, in front of me, which I don't think you can see by video, but everyone is holding up a 3. Maybe you can see me video. So we have 3 lone pairs around that oxygen. Okay, and so this is organic chemistry. We look for these patterns. And so then one thing that's often said about learning is that you should never memorize anything. And I kind of like don't like that phrase anymore. There are some things that we just need to know. So a negative oxygen has 3 lone pairs and 1 bond. And so we just need to know that, but how did we come to know that thing? Kind of memorized it, right? But I hope that there are some things that we repeat so many times, you just come to know it. It's not like you have to like sit down like a day and just try to memorize things over and over again. So it's kind of like the lyrics to your favorite song. So I'm sure all of you have like a favorite song. Was there one day you sat down and decided, I am going to sit down today and memorize all the lyrics to that song? Or did you just gradually come to know the lyrics because you heard them over and over again? And that's organic. So there are some things we just practice over and over again so that you come to know it. But certainly there are advantages to taking that time, that study time where you do just sit down and, okay, I'm going to learn this thing. And so then we repeat it often. So that's some formal charge. But now what I introduced on, let's see, so it would have been Monday, have to remember like what day of the week it is. So what I introduced on Monday was that one of the reasons we have to talk about formal charge is because when we have a molecule that is charged, there is often more than one way to draw that molecule. We have more than one way we can draw it and still fit with our Lewis rules, our octet rules, but we can draw it, draw more than one drawing. So we're going to start, and this idea is known as resonance. So electrons are not confined. We're going to get into that a little bit more after the break. So a thing to remember is that when we do our Lewis dot drawings, we draw little dots, but our electrons don't always have to live right here and draw them on paper. And that is the subject of the second half of class today. Where are those electrons really? But what I want to introduce to you now is that electrons can certainly move around, so they can. And so then that's this idea of resonance. And so we can make different kinds of drawings for structures. Okay, but electrons are confined a little bit in how far they can move. They can only move to the next atom or to the next bond. And so then we need to make sure when we're practicing resonance and drawing new structures that all of our bonding, we still follow all of our rules of bonding. So let's do a practice problem on the left with resonance. Okay, so I am looking at this structure here on the left. What I think is very important to do until you get really comfortable with drawing is that you need to always go ahead and, oh, come on, pencil. You can do it. There's got to be a better way for me to change this. Okay, well, we'll just leave it. Okay, so I'm going to come back to here. There's got to be ways, so the way that we need to do this is to always at first fill in lone pairs. We need to know where all of the electrons really are. So we have electrons indicated in all of these single bonds. But I see nitrogen forms 3 bonds, but we have that octet rule, which means what also exists on nitrogen, especially since this nitrogen is not charged, we're told that in the structure. So there must be a lone pair on the nitrogen. And so when we're doing resonance, it is a good idea until you get very comfortable to draw in all electrons, including the lone pair. Okay, so now I have the lone pairs drawn in. So here's how I go through the process of drawing resonance structures. So we move electrons from high density areas to low density areas. And so then that means we are moving electrons from an area that is negative towards an area that is positive. And that could either be in formal charge or polar character. Okay, so polar character is something you learned about in general chemistry. We'll do a little bit review later, but we also have to think about polar character, which would be dipole negative area towards even a dipole positive area. So that is how we move electrons, always from negative to positive. So in the world of like engineering, something that is positive is thought of as being a hole. So it's a hole. And so it's a hole we have to fill. If any of you have studied semiconductors at all, some of how you talk about a semiconductor is that you're moving things to a hole. And that would be an area where there is positive charges. And so holes don't move. We move things into holes. And so then think of a positive charge as being a hole that we need to fill. In our case, we're filling it with electrons. So positive charges don't move. We move electrons into a positive charge, and so we move electrons in to fill a hole. So that could be a way to think about it, especially that comes from the engineering world. Okay, so looking at my structure here on the left, what is the easiest place to identify? Where we have negative or where we have positive? Yeah, so then Alex said positive. Yeah, because the carbon right here, it has a plus around it. So that's easy to identify. Okay, so do I have electrons in the next atom or the next bond that I could use to help fill that hole? And the answer is yes. So the electrons that can be used to fill a hole are electrons in a lone pair and then electrons in a double bond. This particular problem is practicing with electrons in a double or in a lone pair. So the electrons we can use to move for resonance are electrons in a lone pair and electrons in a double bond. But only from the next atom or the next bond. And I can see I have that here. So I have a lone pair that's neighboring. So we draw electron flow in organic chemistry. Okay, so how we draw that is we start an arrow. Oh, come on. Woo, I think I got it to blue. We start our arrow on the lone pair. So we begin our arrow on the lone pair, and then we say those electrons are going to move into the next bond. We just hop once. So I'm going to take those extra electrons and from the negative region, move it towards the positive region. So this is known as electron flow. Okay, what does that new, rendering, that new resonance form look like? So I have a carbon with its 3 hydrogens still. And then I have a carbon bonded to its hydrogen. But in moving those electrons towards that carbon, what kind of bonding pattern did I create between the carbon and now its negative, or its neighboring nitrogen? It now has a double bond. Exactly. I've moved 2 electrons into between the bond. And so I now have a double bond between the carbon and nitrogen. That nitrogen is still bonded to 1 hydrogen because I don't break any bonds. And then the nitrogen is still bonded to the neighboring carbon and 3 hydrogens. Okay. Oh, I keep moving my little H's around. Okay. if in that original drawing, it was a carbon, if that carbon were drawn with a negative charge, that would mean it had a lone pair. But instead, in the original drawing, that carbon is indicated as being positive. And so that means it does not have a lone pair. And so then that also does mean that carbon is not stable because it does not have its full octet. And so we would expect that carbon to be doing chemistry. And that's correct. Exactly. Nope, it would be negative. And so what we can do is if you want to save that question, what we'll do is we'll address that during break. So that's a great question, and I can show you that during break. That'll work really well. And so then we have this new drawing here, but I have something wrong in this drawing. Okay, so what do I have wrong? The nitrogen needs a positive charge. Yep, so when we do resonance, the overall charge always has to stay the same. And so I have to finish up this drawing by making that nitrogen also positive. So again, nitrogen normally forms 3 bonds, and it normally has 1 lone pair. But in doing this resonance, how have I changed the pattern of nitrogen? That nitrogen now has 4 bonds, and it has 0 lone pairs. And so then that means the nitrogen is not neutral. And what does it have to be? It has to be positive. Okay, and so I'm telling you that now. I'm going to, and this could be another question that comes up in break. If this is a pattern again that I just know, we can during break do the math on this nitrogen if you would like, so as to prove that it really is positively charged. But for now, maybe you'll just believe me that a nitrogen's 4 bonds, no lone pairs is positively charged. Okay, so then what we have down here is called the resonance form. Okay, so we have a new resonance form that we have drawn. I am sure your notes probably look a lot neater than my notes since I can't seem to get out of pen mode and move into pencil mode. Okay, so yours probably looks prettier. That is known as a resonance form. And then you might wonder, why do we even care? Why do we care about 2 different kinds of drawings? And so here's like the big picture reason why we care. When we see that a charged molecule has resonance, that means it is more stable than we would otherwise predict. So it is. It has more stability than we would otherwise predict. And the organic chemistry class is all about chemical reactions. So if a compound is more stable than we would otherwise predict, is it going to do chemistry easily? No, it's not, right? Even though we see that, oh, this molecule is charged, by figuring out that there is resonance, resonance is a stabilization factor. And if a molecule is relatively stable, even with a charge, it is not going to participate in chemical reactions. We get into chemical reactions when we hit chapter 4. So we have a little bit to go before we start actually looking at reactions. But right now we're learning how we predict whether a chemical will have a reaction or not. Okay, let's go to our second problem. We're getting close to break. So we're going to go to our second problem. So I'm going to erase all my scribblings. We'll come back. So here I have a second problem on the right. Okay, so now I'm to this problem here. Okay, and here it's indicated carbon with a negative charge. So what's different about this carbon? Yeah, this carbon must have a lone pair. A carbon 3 bonds and a negative charge absolutely has a lone pair. Okay, and so then, like I said, I recommend drawing in all lone pairs at the very beginning of solving resonance. So then if I move to the next carbon, so I'm right here at this carbon, oh, well, that was funny. Oh, I lost all my drawings. We'll get this figured out eventually. Okay, so then I have my lone pair here. The next carbon has its normal 4 bonds. This nitrogen has 3 bonds, but I know it's not charged, so how do I make up the full octet for this nitrogen? Yep, it also has lone pairs. Okay, is there a resonance form? So I'm going to give you that answer first. Is there a resonance form? The answer is yes, there is resonance here. It is not as obvious. What I highlighted is that we're always moving from negative to positive. Well, I can clearly see negative. So is this side over here positive? Kind of. Okay, it's not as obviously positive. Okay, but I'm going to tell you this does have resonance. And for your first set of problems, as we're learning organic chemistry, this is going to be how it always is. If I ask you to draw resonance, I am telling you, yes, there is a resonance form, you have to draw it. So later, we will get into like complicated structures where it's like, well, is there one or isn't there one? And then, okay, if yes, what is the drive? But for now, we're only going to work on structures that do have resonance. Okay, so let's go ahead and draw the resonance. So I have obviously extra electron density on this carbon because it's negative. So I move into the next atom or the next bond. So I'm going to take those negative electrons and put them into the next bond right there. So we just hop it once. Yeah.
How do you know if it's the atom?
Oh, so it's always just so if it's on the atom, great question. So for those of you who are online, you might not have heard the question. So the question was, what if, so how do you know if you move the electrons to the next atom or the next bond? We move to what's next. So these are electrons on an atom, so then I'm moving them to the next bond. Okay? Okay, but if I can't stop there, because how many electrons would that put around the carbon? That would put like 10 electrons, like 5 bonds around the carbon. If I stopped it there, is there such thing as a 5-bonded carbon? Never. So I can't stop moving electrons there. So that means that right now, this carbon here has too many electrons added. So I have to move electrons away. So now I go from the next bond, I move one set of electrons, because keep in mind, I can move electrons in lone pairs and in double or triple bonds. So I move electrons from lone pairs or multiple bonds. And so I'm going to move one of the multiple bonds away, and then I am putting those electrons onto the nitrogen. So now I'm going from bond to atom. Does that make sense? Yeah. So it's either atom to the next bond or bond to the next atom. So this is the flow. So now what does this new structure look like? So I'm going to give you like 30 seconds as a head start to draw out what this resonance form looks like. Oh, this is where all of you said, wait, what if I do something wrong? I left out an atom. Okay, so it should look something like this. A CH3, a CH, double bonded to a C, double bonded to an N. But our other rule is that the charge never changes. So in this top structure, the carbon was negative. In resonance, I have to have a negative somewhere. What atom is now negatively charged in my second drawing? Nitrogen. Yeah, exactly, the nitrogen. Thanks for the online answer. That was great. Yeah, because what do I see here? This nitrogen is not in its normal bonding pattern. Nitrogen normally has 3 bonds, 1 lone pair, and I see here 2 bonds, 2 lone pairs, and so that means absolutely this nitrogen has a charge. And now we are learning that a nitrogen that is negative is 2 bonds and 2 lone pairs, so that nitrogen is negative. Okay, I'm going to just do one last concept, and then we will take our break. So for the next concept, take off my annotations so I can change to the main page, which is that when we do multiple drawings, we also like to identify a major resonance form. So the molecule exists in both forms, but it's like a 50-50 or a 75-25 or maybe even a 90-10 sort of form. So how many molecules exist in each form? We like to identify the major resonance form. And I always go by bullet point number 1, which is that the charge is on the most electronegative atom. And it doesn't matter whether it's a positive charge or a negative charge. The major resonance form is going to be the form where the charge is on the most electronegative atom. Almost always, this is the only rule we need to think about. Okay, so go ahead and look at your very first drawing. I'm not going to go back in my page. I'm going to let you look at your notes with our first practice problem. Was it resonance form 1, the one that I drew, or resonance form 2, that would be the major resonance form, following this rule? Yep, so then it's number 2. Because what atom was positively charged in that second resonance form? The nitrogen, right? Yeah, the nitrogen. So here's how you can think about it. Nitrogen is an electronegative atom, so it is stable with a negative charge. Also, since it is an electronegative atom and has dipole negative character, that dipole negative character can help to balance out a positive charge. And so that's why nitrogen is relatively stable even with a positive charge. So it has dipole negative character that can help kind of balance out that positive charge on it. Okay, so in our second practice problem, okay, so actually let me come back to the first practice problem. And so if I had you predict what would be the ratio of molecules existing in one resonance form or the other, if I were just doing an off-the-cuff prediction, I would say, maybe 70% of the molecules exist in resonance form number 2, and 30% of the molecules exist in resonance form number 1. So that's just an off-the-cuff, off the top of my head prediction, okay? And so then let's look at your second practice problem. Again, I kind of go, that looks to be like a 70-30. And prediction is something you will gain with time. I've been doing organic chemistry for many years. In fact, longer than some of you are old, right? So I have very good prediction power, and you all will get better. So I would also say 70-30, but which resonance form do I think will be the 70% resonance form, the 1 or the 2? Yeah, the 2 again, because now I have the charge on the most electronegative atom. Okay, there are a couple of other rules, and so then we can look at it has as many octets as possible, has as many bonds as possible. So sure, we can use those, but almost always I just look for where is this charge? And is it on the electronegative atom? And then that solves the problem for me. Okay, so resonance practice. We're not going to get to more resonance practice right now. This is something that I think that we'll pick up on Monday after you've had a chance to do more reading. Or I might have a chance to like send you some extra resonance that you could do like at home over the weekend to get ready for Monday. So we're going to go ahead and move on to our next topic, but after a break. But I want to do a so far, what have we done kind of today? So we have learned where electrons are in three-dimensional space surrounding an atom. So that was last Wednesday and Monday. We've learned how to draw out on flat paper how atoms aggregate. And then now what we're headed into after break is how to draw out the third-dimensional structure of the aggregates. Okay, so we're going to learn how to draw in 3D now that we've done some practice just with like lines and dots. So we're going to do some 3D drawings when we come back from break. So what we're going to do is about 17 after, we will go ahead and reconvene class. So feel free to go ahead and take a few minutes. I'm going to again grab coffee. You can walk outside and get the mask off for those of you who are in here. And then at about 17 after, we will reconvene. Okay, I'm going to put back onto resume. So now I need to come to Teams and now make this larger. We're going to move into molecular structure. So we're going to move into drawing shapes of molecules. So in the world of organic chemistry, how we draw, the method that we use for drawing organic molecules is called the linear combination of atomic orbital like theory. So this is the theory that guides how we draw the shape of molecules. So the theory is known as the linear combination of atomic orbitals, or LCAO theory. So then this is the theory that we use on how we visualize the shape of molecules. Because until these last several years, so sure we have all of these like online programs and balls and sticks, and some of you have used Spartan, and we have visualized the three-dimensional shape. But how did we, even as chemists, decide that that is accurate? And so chemists years ago developed this theory, and so using this theory is how we develop these 3D renderings that you now create. Okay, but I need to be able to get all of you to the point to where without a computer program in your head, you can visualize a molecule. And so then that's why we're going to start learning about this theory like at the very basics. Okay, so what I want you to do is I want you to think about the story I'm presenting here. So you'll notice in my PowerPoint that there are many times to where there's a story that I want you to understand so well that I write out my words. So of course, in doing this, I violate all those good rules of PowerPoint of having pictures and no words, right? But sometimes I really want to make sure that you know my words. So let's go ahead and go through my story. So let's imagine H2, the H2 molecule. So that molecule results from the linear combination of a 1s orbital from one hydrogen with the 1s orbital from another hydrogen atom. Okay, so then that's what that molecule looks like. Okay, so then what does the bond look like between the two atoms? So what does that bond look like between the two atoms? So what I have visualized up here is on the left a circle and on the right a circle. And so then when I form a bond, and maybe some of you can see me online, you can tell me later whether this is working or not. Okay, so we're going to take these 1s orbitals and we're going to linearly combine them, which means we're going to take them and we are going to overlap them on top of one another. That's what linear combination is. We're going to overlap them on top of one another. So in your mind, can you picture these two balls coming together? And then what is the shape that results from that? Okay, but wait. While you're doing this, we also need to get back to Schrodinger's equation. So we talked about mathematical symbols, remember that? So we always have to think about that this theory is based on math. And so we have an s orbital of the positive waveform that is going to come together and linearly overlap with another s orbital of the positive waveform. Okay, so I'm going to add just a little bit to my picture here. So like if you're drawing this in your notes, what you can do is add a plus here and a plus here. These are math symbols, not charge, math. So I'm going to overlap a plus with a plus. Okay, this would be like taking a crest of a wave and overlapping it with another crest of a wave. Because remember that Schrodinger's equation, orbitals, it's all about wave math. What happens when two waves crash together? They make a bigger wave, right? You can go to pictures in like Florida right now and see all of the big waves that are happening, and waves are crashing into waves as we have these storms moving in. Okay, so if I have a crest hit a crest, mathematically, what is that going to look like for our molecules? So I'm going to take us to the next picture. I think I'll take us to the next picture. Okay. Right here. Okay, there we go. This is my picture of what it looks like. So I have an S, a crest of a wave, crashing into another S that is a crest of a wave. Crests adds together, and so what does the H2 molecule look like? It looks a lot like this larger blob that I have up here on the page. Okay, so I have a circle that is overlapped with another circle. I add together, mathematically add together the probability of finding electrons here in the middle. And so then that's why I have a larger kind of like a concave area here. I've added electron density probability together. I drop down and then I come back around. So I get this shape. So this is the shape of the chemical bond that forms between two hydrogen atoms. So this is the shape of the chemical bond. And since H2 just has two atoms, this would be the shape of the molecule. So what I want to highlight about like this linear combination of atomic orbital math is that are the electrons actually confined to just between the two nuclei? They're not. So the electrons can be anywhere in that three-dimensional space. Where am I most likely to find those electrons? So it's kind of like, where is the area the largest, the widest in the shape, in between the two? So that's my highest probability of where I'm going to find those two electrons in an H2 molecule. But they can be anywhere within that three-dimensional space. So then that would be the 3D shape of the molecule. Okay, so now let's get to my statement at the bottom, which is really important about how we talk about chemical bonds. So a covalent bond is formed when an orbital with one electron constructively overlaps with another orbital with an electron. So let's talk about a constructive orbital overlap. So constructive overlap is when you have a positive waveform crash into another positive waveform, or a negative crashing into a negative. Okay, so I could change the mathematical symbol here. I could make this a minus crashing into a minus, and then overall the waveform here would be a minus. So this would be a trough of a wave meeting another trough of a wave to make a deeper trough. But keep in mind that we have to flip our trough in all 3 dimensions. So it would have like the same shape. So constructive overlaps are when orbitals of the same form crash into one another. And we call that a bonding molecular orbital. And then that bonding molecular orbital would be filled with some electrons. Okay, but we have 2 different waveforms, right? We have 2 different forms of the wave. So this is what gives us a sigma bond. So S plus S is a sigma bond. So it's known as a sigma bond. Okay, but, so I just have talked about a plus overlapping with a plus, or a minus overlapping with a minus, and it gives us like this shape, a good chemical bond. But what is the other possibility that can exist? Yeah, a plus overlapping with a minus. Okay, so then let's go ahead and look at that, because we have to consider all of the different possibilities that could exist. Okay, so the other thing that can exist when 2 orbitals approach one another is that one orbital could be in its positive wave form, and that I'm indicating in blue. So in your notes, you could draw a circle with a plus. And the other possibility is that it could overlap with an s orbital of the opposite wave form. So mathematically, that would be a minus. And so what if we had a hydrogen atom in its positive form interacting with a hydrogen atom in its negative wave form? This would be like the crest of a wave meeting with a trough of a wave. And then what happens if we do linear combination? So we just mathematically combine a plus with a minus. What happens when we combine those 2 kind of mathematical numbers or those 2 kinds of waves? However, it's the easiest to think about it. What's going to happen when we do that combination? We end up with like what number? So a plus 1 added to a minus 1 is going to give us what number? A 0, right? So that a crest meeting a trough cancels each other out. So what we know can happen is that when we form molecules, we can have a positive orbital interact with the negative form of another orbital, and they would cancel out in between. And that chemical bond that forms between them would have and then that molecule would have a very different shape. So we cancel the electron density in between. So that's the black area that I have indicated in between the 2 s orbitals. So that would be this area right here. I cancel electron density, the probability of finding electrons. And so then that means I create a node. A node actually is created between those 2 atoms. So this kind of bonding is still known as a sigma bond. But I've done destructive orbital overlap because the 2 orbitals were in the opposite wave form. And when this happens, we give that kind of bond a different name. We call that an antibond. And then we refer to this kind of bond as a sigma star bond, if we're just writing out like little notations. So we would write it out with letters as an antibond, so ANTIBOND, so on and so forth. But if we're drawing out this kind of a bond and just making like notations, we do do a sigma and then a star to say I have an antibond here. Okay, so now, where are the 2 electrons of this bond? Actually, better yet, here's the question. Are the 2 electrons in this bond nicely shared between the 2 nuclei? No. It often can be the case like 2 are on one side, none on the other. 1 electron's on one side, 1 electron's on the other. We actually don't know how electrons move. All we know is the probability of where we find them. Well, we probably find electrons between the 2 nucleus. So how strong is the chemical bond of an antibond? Is this a strong bond or a weak bond? It is very weak. And so then generally we do chemistry to form strong bonds. So even though we have drawn out this antibond, do we very often form antibonds in reality? No, there is a chemical possibility, but do we tend to form them? No. When we do chemistry, we tend to form actual constructive overlap covalent bonds. We tend to not form antibonds. And this is where kind of like the idea of antimatter came about. Okay, so Star Trek, right? That's Star Trek. I'm not getting it wrong. Okay, so Star Trek, we have like antimatter. And so how would one create antimatter? If you could bring together and only form antibonds, you would have antimatter. But can we do that yet? No. But would it be very high in energy? Absolutely. Because these would be very unstable kinds of matter if we actually formed them. It would be very high in energy. But we can't actually do that yet. So there still is no such thing as antimatter. But you can, that might help you think about this idea of antibonds. So there is the theoretical possibility antibonds could exist. We could bring together atoms all antibonded to make antimatter. It would be extremely high in energy. And I think I even have that on the next table. And so when we think about our bonding and our energy diagrams, our energy diagram would look like this. So when we bring together s orbitals, if we bring them together constructively, both of them in the same wave form, we would form what we call a sigma bond. And that sigma bond is nice and low in energy because now electrons are paired. So I have 1 electron from an s orbital, 1 electron from another s orbital. I bring them together, they're paired in a nice covalent bond. Okay, but what is the other possibility that exists? I bring them together in an antibond. I create a node in that process of antibonding, and that's a very high energy orbital. And normally we do not form that kind of molecular orbital. And so then how we can think about like electron configuration is I have 1 electron in the 1s. I have another electron on this 1s. I bring the 2 electrons together. 1 goes here, 1 goes here, that property of opposite spin. And normally this sigma star molecular orbital is empty. It has no electrons in it. And so then that means that that property, that character does not contribute much to the overall character of the molecule. The molecule tends to stay nice and stable. Okay, so that's S plus S. But what is another possibility that exists? We're going to go through all of our different possibilities. And again, today I'm going to do this pretty quick and we'll revisit it just a little bit more when we come back on Monday, but this gives you a chance to like do some reading to kind of gain a greater understanding of things. And so the next possibility that exists is I can do an S plus P. This would also form what we call a sigma bond. So on the page in front of you, how do I have this overlap set up? So linear. And so there are 2 linearly combining, so an S coming in linearly with a P. And I have the S in its positive waveform, and I have the P orbital oriented to where positive waveform is on the left, negative waveform is on the right. What kind of orbital overlap am I kind of setting up on this page? So in your mind, when you bring these together, am I going to have constructive or destructive? How have I set this up on the page? Constructive, yep. Because I'm just going to bring them over and then barely overlap them a little bit. So I'm setting up a constructive orbital overlap. And so then what is that shape going to look like? And it's like this. So on the left, I'm kind of showing you like literally the two overlap on top of one another. Where we have regions of overlap, the probability of finding electron density grows. And so when we form an S plus P sigma bond, on one side of the lobe, we grow that lobe larger. And then on the other side, it's a little bit smaller. Okay, so for this kind of chemical bond, what that would mean is that we have more probability of finding electrons between the two nuclei than like over here on the far side of one of the nuclei. So then the little gap here is more just, I want to highlight that right at the nucleus, there is a node. So right at this, so at our nucleus on the left, we have electron density completely surrounding that nucleus. But then right at this second nucleus, there is a little bit of a node. So that is why I have the gap. There is a node in the second nucleus. Okay, but then again, the take-home message is that I tend to find electron density between the two nuclei. But there is always the possibility that the electrons could be like on the far side of one or the other nuclei. Okay, so then that is a sigma bond, so a constructive orbital overlap to form a sigma bond. But what else theoretically can happen when I bring an S and a P orbital together? So instead of doing constructive orbital overlap, I might end up doing, and everyone says, destructive orbital overlap. Okay, and so then what would that look like? So on my page, how I have that set up as a picture is like this. So I kept my S in the positive waveform, overlap it with a p orbital with negative on the left, positive on the right. The destructive orbital overlap would give us what we call the sigma star bond, the anti-bond. And then what would be the shape of that kind of chemical bond? So I'm doing like all of these drawings totally visually. If we were to solve exactly for Schrödinger's equation, which computer programs can do, they give a shape very much like this. And so then on the far left-hand side, I have the positive overlapping with the negative. And so then that's going to cancel out. So right here, I cancel out all the probability of finding electron density so that that gives me a new node. And so then the left-hand side of the s orbital, or sorry, yeah, the left-hand side of the s, the left-hand side of the p orbital, those areas become smaller because mathematically we're doing some subtraction. And so then that would be why this is a little bit smaller, this is a little bit smaller. But then I'm not affecting this other side of the p orbital lobe at all. And so then that is why it is the same size over here on the right. So that would be the shape of that chemical bond. Okay, so thoughts. We always have to get to what's the big picture. So if I were to form an S plus P sigma star bond because of destructive orbital overlap, is this going to be a very stable bond? No, not at all. It would be a very unstable bond. And so then again, getting back to big take-home message, are we normally in the course of our chemical reactions going to form this kind of bond? No. So normally we're not going to be forming this bond, but we still talk about it as a possibility. Okay, so we've done S plus S, constructive and destructive, to give us a sigma bond. S plus P, also constructive, destructive, to give us a sigma bond. So then what is the last combination that is relevant for the field of organic chemistry? P plus P, exactly. So now let's go ahead and look at a P plus P orbital overlap and what that is going to look like. Okay, sorry, I forgot energy diagram again. And these are all repeated in your book, so you can look at your book for these energy diagrams. So I can have a 1s electron coming from the s orbital. I would have another electron coming from a p orbital. I can form a low energy sigma bond with the electrons pretty well shared between the two nuclei, or I can form a high energy sigma star bond with electrons not hardly shared at all between the two nuclei. So now let's go ahead and jump to P plus P. So for P plus P, that kind of bonding we know exists only as I have it pictured on the page. So when a p orbital overlaps with a p orbital, linearly, it is always parallel side by side. So they come together parallel side by side. That is always how a p orbital overlaps with another p. This kind of orbital overlap is given a different name, so it is given the name of pi. It is a pi type of bond when we do overlap of a p versus p. So it forms what we call a pi bond. So how have I, on the page in front of you, arranged this pi bond? Have I arranged it so in your mind, see those two orbitals beginning to come together? So on the page, how have I arranged this, constructive or destructive in my drawing? Yeah, constructive. Okay, so then let's go ahead and look at like my rendering, which isn't all that pretty. Here's my rendering of a constructive orbital overlap between two p orbitals when I bring them together. So one thing that I'll have you notice about like one of the big differences in a pi bond is that we do not have any orbital overlap in between, right? So there's nothing in between, right, directly between the two nuclei. And so that is one of the reasons why it is given a different kind of a name, pi. So these are called pi bonds. So they look very different than sigma bonds in that we don't have any electron density directly between the two nuclei. But instead, we get overlap of electron density above, and we get overlap of electron density below. And so sometimes, like if I have a carbon to carbon, like pi bond, sometimes what's simply done on a page is we draw two carbons, and then like this above and like this below. It almost kind of looks like a hamburger. Right, and so then that's to represent I have a pi bond between those two carbons when we do that kind of representation. Okay, and so then it's a sigma bond. One of the reasons we call, it's a pi bond. One of the reasons we call it pi is because it looks very different. We don't have electron density directly between the two nuclei. And then you can see that where we tend to find our electrons are kind of in a region above the atoms and in a region below the atoms. Okay, so then that's the constructive orbital overlap. And then what does destructive look like? Oh, it looks really funny. So for our destructive, it would be arranged like this. So I have like a head to tail arrangement of the p orbitals on the far left. I have waves crashing into troughs everywhere. I form a new node And so then this is kind of the shape of a pi star bond, destructive orbital overlap. And so wherever in my picture I have negative overlapping with positive, I get cancellation. So up here and then down here, so I'm drawing arrows on the page, I get cancellation of electron density. Whenever I cancel electron density, I get a node. So what I'm trying to show you here in this picture is I canceled out like all that probability of finding electron density all through the middle, but I kind of like kept the little swoopy on the left, I kind of kept the little swoopy on the right, and then canceled all of the other electron density in the middle. And so sometimes how people will literally draw this is like I have a nucleus. Here's my nucleus, and then it kind of looks like that on one side, nucleus, and like that on the other side. Okay, so organic chemists are always not artists. So we do our best that we can with these visual drawings, but they're not going to be perfect. Okay, and so then this is getting at how we draw 3D pictures. So I'm going to go ahead and take just a couple minutes because we're almost at the end of class time to give you the preview for Monday so that you know like where you can be reading. And so then our preview for Monday is this. So we're going to learn how to like draw molecules. Easiest to draw is like a hydrogen, H2. Drawing CH4, much more complicated. If we draw all of the bonds and all of the anti-bonds, this would be all of the drawings for CH4. But what we're going to focus on is just drawing the bonds. We're not going to worry about drawing anti-bonds. We're just going to draw the bonding patterns. Okay, and so I'm going to take you way forward. We have a few more things to do, but if you want, you can come to this page over the weekend. So for our drawings, we're going to think about the shape of the orbital, and that's going to be on the far left. So when we bring all of those orbitals together, what does that begin to look like? And so then that would be like my middle picture and my ends picture. And so on Monday, we're going to be doing lots of drawing, and in our mind, we're going to be bringing these orbitals like all together in three-dimensional space to give good pictures of our molecules. Okay, so then that is where we're headed on Monday, is drawings of molecules. Okay, so have a great rest of your day. I'm going to begin to get all of my recorders off. Have a great rest of your day today, and then I will see you on Wednesday.